So now we learned how we can convert an alkene into an anti-1,2-diol. But how can we produce also syn 1,2-diols? And I can tell you, yes, we can. And therefore, we need to perform a so-called pericyclic reaction. And what is now a pericyclic reaction? If you have to describe what is a pericyclic reaction, you could say it is a concerted, so single-step reaction which proceeds over a cyclic transition state. And, well, the most common pericyclic reaction is the so-called cycloaddition reaction. And here the carbon-carbon double bond of an alkene reacts with another molecule to form a cyclic product. Here we will have a look on pericyclic reactions of alkenes with osmium tetroxide. And if we use osmium tetroxide to convert an alkene into a 1,2-diol, it is a so-called dihydroxylation reaction. And what is now the trick in this reaction? It is very similar to the formation of the anti-Markovnikov product. So we add two oxygen atoms at the same time so that they can come from the same side. And in this way, we can achieve a so-called syn addition. So let's start with the reaction mechanism. So first of all, we have osmium tetroxide. This is this molecule. Here we have osmium in the oxidation state 8. And you can see that we have 4 oxygen atoms connected to the osmium with each with a double bond. And then, for example, we can use a transalkene, and this is our starting point. So then we already know that the nucleophile will be the carbon-carbon double bond, and we can see here the red arrows which indicate already what happens. So we approach with the transalkene to this osmium tetroxide, and then the double bond of the alkene will attack one of the oxygen atoms of the osmium. And then further on, we will see that one electron pair then moves towards osmium, and at the same time, another electron of a neighboring osmium oxygen bond will move to form a new oxygen-carbon bond. And this reaction is then the so-called cycloaddition. And as already said, it is a one-step reaction. That means it is concerted. And concerted means that all these steps, what we just saw, will take place at exactly the same time. Then we have this cyclic transition state where we indicate the new or broken bonds already with the dotted lines. So you can see you have a 5-membered transition state, and the 6 electrons are delocalized around this ring. Then after this transition state, we cleave and form the new bonds finally, and then we end up with this osmate ester. And here you can see that the osmium is now reduced. We only have oxidation state 6 instead of 8 as we started. And also important, the new carbon-oxygen bonds here are on the same face of the former carbon-carbon double bond. And hence this addition is a syn addition. Usually this reaction is carried out in water. Hence, our osmate ester will directly react in a hydrolysis where the 2 osmium oxygen bonds here will be broken, and we form this 1,2-diol, which is our desired reaction product. And then, besides this 1,2-diol, we will also form another osmium product where the osmium is still reduced in oxidation state 6. And if you have a closer look on our product, you can see that both hydroxide groups are now on the same side. That means we have our desired syn addition. What you should note is that this dihydroxylation is a stereospecific reaction, and the osmium tetroxide can react equally well with both sides of the carbon-carbon bond. So this means that our osmate ester will be formed as racemate. Well, this is now how we can produce syn 1,2-diol. And in principle, we now have a good way how to synthesize syn 1,2-diols, but the problem is that osmium tetroxide is not only expensive, but also toxic. Hence, it is required that we can minimize the amount of osmium tetroxide. And to achieve this, there are usually oxidizing agents added to this reaction. And what does this oxidizing agent now do? As soon as osmium is reduced from oxidation state 8 to 6, the added oxidizing agent will selectively oxidize osmium back to osmium tetroxide with an oxidation state 8. And hence, we only need a very little amount of osmium tetroxide for this reaction. What is usually used as oxidizing agent is this potassium hexacyanoferrite. And of course, this is not the only oxidizing agent. You could also use other oxidizing agents, for example, periodic acid. But with periodic acid, you now have another problem. And the problem is that periodic acid can also oxidize the 1,2-diols and hence forms carbonyls. So this means that we can minimize the amount of osmium tetroxide, but at the same time, our product will no longer be the desired 1,2-diol, but instead will be an aldehyde and or a ketone. And we will then also form iodic acid. Here you can see the reaction which can take place if we use periodic acid. So we have our 1,2-diol, which is formed, and then we add this periodic acid, and we will form, similar to the pericyclic reaction we just saw, periodate ester. But then, unfortunately, we destroy our diol and form the ketone and the aldehyde as well as the iodic acid. And because this reaction is an oxidation with periodic acid, where the carbon-carbon bond is cleaved in the 1,2-diol, this reaction is also called oxidative cleavage. What do we now know? And most of the time it is better to add potassium hexacyanoferrite as oxidizing agent instead of periodic acid, because then we can minimize the amount of osmium tetroxide which is needed for this pericyclic reaction to form our desired syn 1,2-diols, and we do not have the problem which we have with periodic acid, that we can destroy our desired product with an oxidative cleavage reaction. And there's also another way how to produce syn 1,2-diols, and this way is the reaction with potassium permanganate in a cold reaction. If we don't want to use osmium tetroxide to produce syn 1,2-diols, we can also use a cold and diluted potassium permanganate solution, which then reacts with the carbon-carbon double bond in a pericyclic reaction to produce, after a subsequent hydrolysis, the 1,2-diol also in the syn configuration. And the reaction with potassium permanganate is very similar to that of osmium tetroxide. And again, the reaction involves a concerted cycloaddition, which produces then, in this case, a manganate ester instead of the osmate ester. And yeah, let's have a look on what is happening. So we start with the permanganate, where manganese is in oxidation state 7. And then we approach with a transalkene, similar to what we just saw with osmium tetroxide. And again, this cycloaddition is a concerted one-step reaction mechanism. That means we start with the nucleophile, which is our carbon-carbon double bond, which attacks one oxygen atom of the permanganate, and at the same time, an electron pair of the oxygen manganese bond will move towards manganese, and another neighboring manganese oxygen bond will start to give their electron pair to move towards the carbon to build a new carbon-oxygen bond. And again, all these steps are taking place at the same time, and we enter a so-called cyclic transition state where we have this 5-membered ring and the 6 electrons are delocalized around this ring. And after this cycloaddition, we end up with manganate ester, where manganese is reduced towards oxidation state 5. And we now have 2 new carbon-oxygen bonds here, which are formed on the same face of the former carbon-carbon double bond. That means we have a syn addition. And this reaction is usually carried out in the presence of aqueous hydroxide. That means the just formed manganate ester will immediately be hydrolyzed towards our desired 1,2-diol. And manganese will be reduced from oxidation state 5 towards oxidation state 4 in the final manganese dioxide. And what is now important, this cycloaddition proceeds in one concerted step, and both the manganate ester as well as our final 1,2-diol retain the configuration of the starting alkene. So hence, if we start with a transalkene, we will produce a trans 1,2-diol. And therefore, this reaction is steric-specific. And you should be careful, because you saw here that we started with our transalkene, and then we end up with the trans-diol. And now do not mix up the position of the R groups, which indicates here that we have a trans-diol, with the fact that both hydroxide groups are now on the same side. So the fact that we have 2 hydroxide groups on the same side is that we have a syn-diol, which is produced in a syn addition reaction, but still our R groups are on different sides. That means we have a trans 1,2-diol. Also, similar to the reaction with osmium tetroxide, both the manganate ester as well as the 1,2-diol are formed as a racemate. And the reason for this is now that the potassium permanganate can react equally well from either top or bottom face of the carbon-carbon double bond. Hence, we will end up with racemate, which is an equal mixture of 50% and 50% of both enantiomers. And very important here is, for obtaining the desired 1,2-diols, the reaction must be conducted in a cold medium. And the reason for this is that potassium permanganate is such a strong oxidizing agent, which will otherwise oxidize the 1,2-diols towards ketones and carboxylic acid. If we do have higher temperature, that means if we have temperatures which are like room temperature or even above. So the reaction, or the pericyclic reaction of alkenes with potassium permanganate in a cold reaction medium can therefore be used to produce 1,2-diols with the syn addition. And what happens now if we have higher temperatures, like room temperature or even above? You can see here that we start with our 1,2-diol, which then reacts with the very strong oxidizing agent, our potassium permanganate, and will end up with a ketone as well as an aldehyde, where the carbon-carbon bond of the diol is now cleaved. In case we have an aldehyde, the potassium permanganate will further react with this aldehyde, and the resulting product will then be the carboxylic acid, as the potassium permanganate will oxidize the aldehyde further. That means if we have not a cold reaction medium but room temperature, or even a temperature above room temperature, the potassium permanganate will induce the oxidative cleavage of the 1,2-diol, and then we will end up with ketones and carboxylic acids.